Welcome back, class. So today we are going to talk about bond energies and how we can use these values of bond energies to calculate the delta H of reaction, the enthalpy of reaction. So yet another way that we can calculate the enthalpy of reactions. And this will allow us to then look at how strong bonds are and some trends in bond strength, and also looking at bond length, how long bonds are. So let's focus on this idea of bond energies. So, of course, the bond energy is the energy of the bond, right? So in other words, how much energy it takes to break that bond, or how much energy is released when we make that bond. And of course, actual bond energies will depend on other bonds that are surrounding, the atoms involved, etc. Now, what we have listed in the tables are what we call average bond energies, right? So these are when we look at, the same bond, meaning between the same two atoms in different environments, and we sort of take an average of what it is, of all those different environments. So we take into account that, sometimes it's, part of a structure where there's a couple other bonds, to the same atom, or and those atoms might be different, and so forth. So we look at that same bond in various structures, and we take an average of the bond energy, and those are the values that you'll find in tables. Now, those values, like a lot of the values, are done, quote, in the gas state. So this obviously works best when everything is in the gas state, and so we don't have to worry about any sort of issues with what we'll learn about is intermolecular forces. So we don't have to worry about the molecules interacting with each other. In a gas phase, there really are no interactions, and so we can kind of simplify the situation. So that's why a lot of these, quote, ideal values, then we see these trends, are in the gas state, like ionization energy, etc. Now, the things that you're going to want to remember here, and these are sort of your governing principles, is that every time you break a bond, it is endothermic. So it always takes energy to break a bond. So, while it's tempting to think about the idea that, we talk about bond energy being stored in the bonds, right? So what that kind of connotates is if you break it, you release it, right? And that's not the case, right? When you break a bond, it always takes energy. Just think about breaking anything. If I break a pencil or break, a rubber band, it takes energy to do that, right? I have to input energy to break something. So breaking a bond is always endothermic. It means it always has a positive enthalpy value. Bond making, on the other hand, is exothermic. So bond energy is always released when we make a bond. And so bond making always has a negative change in enthalpy. So breaking a bond is always a positive enthalpy change. Making a bond is always a negative enthalpy change. So the formula that we use, right, is that we take all the bonds that are broken, and we take the values from the table, and we use the positive version of that value. We look at all the bonds that are formed. We add up all those using the negative of the same value in the tables. And we take the value of the bonds broken, we add it to the value of the bonds formed, and the overall change is going to tell us what the enthalpy change of the reaction is. So the idea is we're going to have a large positive number here, or we're going to have a positive number. We're going to add it to a negative number. So whichever one of these is bigger, right, is going to determine whether my delta H of reaction is overall positive or negative. Or in other words, is it an endothermic reaction? Right? If it takes more energy to break the bonds than what we get back when we form the new bonds, well, then it's an overall endothermic. If I release more energy when I form the bonds than what it cost me to break the bonds in the reactants, then I have a negative value. I get an exothermic reaction. So that's how all this will work. So this is going to give us yet another way to calculate enthalpies of reactions. Now we're just starting with a little bit different data here. So if we look at the table here, we can see all of these different bond energies, right? And they're grouped kind of by an atom and different things that it can be bound to. And so we can see, so when, if you look at the single bonds here, right, they're going to be anywhere from, 300-400, maybe up to 500 and something kilojoules per mole for a single bond. Some much lower than that, some, up to the high end of that. Now, double bonds, right, you notice they're going to be relatively higher in energy, right? If we're sharing 4 electrons, it's going to be harder to break that bond than it is if we just have 1. Triple bonds are even going to be higher energy. So this is where we're going to find those values, and notice they're always in kilojoules per mole, right? Now, I will point out specifically CO2 here. So if we look at a CO bond, double bond here, 736 is the typical value we'd use. Now, in carbon dioxide, we have a higher value. And that has to do with the idea of resonance and the delocalized electrons within carbon dioxide because those bonds are, the electrons are delocalized over those two because of the resonance structures. That stabilize, so it takes more energy. They're stronger in CO2 than they are in, say, some other molecules where you might have a CO double bond. But again, so on other things, these are just averages, right? And it's a close enough average that we can use it in any compound that has that kind of bond. Okay, notice these are positive values, but we're going to use them in either positive or negative values depending on, if we are talking about it being broken or being made. So we can visualize this before we get into calculation. Let's just visualize this. And the reaction that we're looking at here, right, is the reaction of CH4 methane plus Cl2 reacts to give us CH3Cl plus HCl. Okay, so this is that we're looking at. So if I think about this structure, I'm going to go from here. Right? I have to break the carbon-hydrogen and the CCl bond, right? So I have to break this bond, and I have to break one of these bonds. And so I end up with things that look like this. Now, in order to get to my products, right, I have to make this new HCl bond, and I have to form, the CCl bond, and I have to make an HCl bond. So I have to make these two bonds. And so if I were to look at how much energy it takes to break these here, and how much energy we recover when we make these here, and look at the difference, I'm going to get the change in enthalpy, right? So, it's the enthalpy change here versus the enthalpy change here gives me the overall process. And so this is an overall exothermic reaction because we recover more energy. So in other words, we get more energy back here than what it cost us here. And this is what we see in an exothermic reaction, which is what we see a lot of, right? Because, again, a lot of reactions, we're going to get to lower potential energy in our products, or in other words, they're going to be exothermic. Now, let's do one where we put these numbers into use and calculate this. Okay, let's do a problem here. So this is our target reaction here. So we want to calculate the enthalpy change of reaction for this reaction using bond energies. So we have methane plus 2 moles of water goes to 4 moles of hydrogen gas plus a mole of carbon dioxide. Now, in our little sample one that we showed, right, we just kind of looked at what was broken and what was made, and we could just look at certain bonds. Now, truth be told, for most reactions, it's going to be a lot simpler if you just break all the bonds in the reactants and you make all the bonds in the products. That way, you don't have to worry about just doing certain bonds and making certain bonds. And so it's a lot faster if you just break all the bonds in the reactants, get that value, make all the bonds in the products, and get that value, and you compare them. So that's what we're going to do here. So to do that, we have to kind of have an idea of the Lewis structure, right? Because we need to know what bonds and how many of them there are to break. So if I draw out the Lewis structure of these four compounds, I get this like this. So let's first look at the bonds that we're making. Or excuse me, the bonds that we're breaking. So I'm going to break CH bonds here, and I have to break 4 of them, right? So I have to break 4 CH bonds. And over here, I have 2 waters, and each of those waters, I have to break 2 OH bonds. So I have a total of 2 times 2 are 4 OH bonds are what I have to break. Now, if I pull that value out of my table, a CH bond has a value of 414 kilojoules. So 4 times 414 kilojoules per mole plus an OH bond, which if I pull it out of the table is 464 kilojoules per mole. So if I do all the math, add this up, I should come up with about 3512 kilojoules. Whoops, that's kind of right, that little weird looking. Kilojoules. Now notice these are positive values, right? Because it's taking energy to break these. So these are going to be my endothermic values. So let's go over here and do the bonds that we're going to make. So we're going to make an HH bond, and we have to make 4 of them. So we're going to make 4 HH bonds, and we have to make 2 CO double bonds. Because we have 1 CO2, so let's make 2 of those. Now, again, if we look up in the table, an HH bond is 436 kilojoules. Now, a CO bond, right, is like 736 or 769, something like that. But remember, since we have CO2, we have that special value for CO2. So that's going to be 799. So that's an easy place to kind of get caught up. So just remember, anytime you use CO2, we're going to use that special value. So if I go through this, I should get, now notice, oops, I need to write this in. We need to use the negative values because we're making these, and that's an exothermic process. So we're going to take the numbers, make them negative. So I get a negative 3,342 kilojoules. So now it's just a simple math, right? 3512 plus a negative 3342. I get a negative, oops, equals, let me show it here, negative 170 kilojoules. Now, you could also write this 1.70 times 10 to the second kilojoules, right? However you want to write it. But that's what I'm going to end up with. I'm sorry. Yeah, it should be a positive value. So a positive 170 kilojoules, right? This number's, whoa. Oopsie. Let's draw that again. 3512. Our positive number is bigger, right? So we're going to end up with a positive number. So we get positive 170. So that means this reaction is overall endothermic. by 170 kilojoules. Okay. So that's the idea. That's how we can get through this or use this to calculate delta H's of reaction. Okay, so now let's take a look at bond lengths. So bond length, of course, is the distance between the nuclei and bonded atoms. This is called a bond length. Again, sort of like the bond energies we saw in the last table, we're going to use average bond lengths. So we're going to take this kind of bond in a bunch of different compounds and take the average length of those bonds. And so average bond lengths. Now, if we look at the table, I'm just going to kind of go through here and point out some threads, right? So we can see that, single bonds are going to be, all over the place in terms of length. We got really short ones like 74 up to, maybe 160, 170, maybe even a little bit bigger for single bonds. Double bonds, right? Well, again, they can go from 128, 120, right? They're varied. Now, we have to get kind of careful here when we start comparing bond lengths, because the size of the atom plays a large role, right, in the bond length, right? Because if they're bigger atoms, they have to be further apart. So if you bond to bigger atoms, you're going to end up with longer bonds. So you can't just look at two bonds and compare them, readily, right? You can, and it'll tell you something, but it's not the most useful thing. What we really want to look at is families of bonds, and then we can kind of see some of the trends. So if we look at the difference between a single bond, a double bond, and a triple bond, if we look the same type of bond, what we see is that they get progressively shorter, which is what you would expect, right? Because as you start sharing more and more electrons, the attractions become stronger, right? And so those stronger bonds become shorter. And so that's one of these sort of overall points that we can make, is that stronger bonds are shorter bonds, right? And so we see a double bond get a little bit shorter, a triple bond get even shorter. Now again, you have to be careful on your comparisons. So if I take a single carbon-carbon bond and let's see a single, let's do it this way, a single CH bond at 110 and a double CN bond, right? It looks like the double bond is longer. Right? So you just have to be a little careful and compare families of bonds. Now, another trend you might look at is comparing bonds between sort of within a period on the periodic table. So, for example, we could look at halogen diatomics. So we're looking at FF bonds, CL bonds. So how does the bond length compare as you sort of move through a group on the periodic table? And what we see is that as we go down a group on the periodic table, its bond with the same atom gets longer and longer and longer. Right? Again, this just is emphasizing the idea that atoms get bigger, right? So we get the idea that bigger atoms tend to make longer bonds. And we could see this if we look at, for example, the hydrogen-fluorine bonds, right? Or the hydrogen-halogen bonds. So the bonds to the smallest atom, it's shorter. We start bonding these bigger atoms, they get progressively longer. So bond to bonds, the same type of bond to bigger atoms, they get longer and longer. Okay, so that's a couple things there. So now, to emphasize that first point that I made, is that bond length and bond strength, how do they go together? Well, the biggest thing that we can say about how they go together is as the bond gets longer, the bond gets weaker, right? So shorter bonds are stronger, longer bonds are weaker, right? So we saw that if you go from single to double to triple, those bonds get stronger. That means they're also getting shorter. If we went down the period, those bonds are getting longer. That means they're getting progressively weaker. So if we look at, again, another family, this is nitrogen bonding to the halogens, and we look at the strength, we see that the shortest bond is the strongest, the longest bond is the weakest, right? And that's the size, right? The size gets bigger. And so as you get bigger, your bonds get longer and they get weaker. So those are some of the trends that we want to be able to utilize, and you want to be able to do this in the sense of, if I give you some bonds that you could, based on what we know about the trends, we could say, oh, this bond is going to be stronger than this bond, or sort of like that. So we can rank bonds in terms of relative length and strength using these relationships. All right, so next time we will wrap up our discussions in Chapter 10, and we'll turn our attention and talk a little bit about ionic bonding.